Hi everyone. So this is a video on deep learning, book by Goodfellow, Yoshua Bengio, and Aaron Courville. And so in this video, I'll just be going through the chapters in this book. It will be an overview, and I'm doing this mainly to revise myself of the concepts in it. And yeah, so this video is just made so that I can get better at explanations. But if you find this helpful, then that's all good for you. So come to the first chapter, as we can see here. So it's all about the introduction and the history. So this is called as Moravec's paradox, as you can see. So humans think the way humans think and the way the computers think, they are opposite. So humans, for a baby, let's say, for a just 1 year old baby, recognizing apples from oranges would be very easy for it. But doing any calculus or any math would be almost impossible for the baby. But for a calculator, if you take a calculator, which is the dumbest computer today, that can do all the calculus and a wide range of mathematical calculations, but it will not be able to do any kind of image processing. And image processing takes a lot of GPU and a lot of computation. So what I'm trying to say is the approaches to solving things, the approaches to thinking is kind of a reversed way. So as you can see here, so it can also be called as a Moravec's paradox. Now you can look it up later. So going to the next part here. So yeah, so and again, I will be just skimming through this chapter and the other chapters in this series of lectures. And like I said, this is just an overview or kind of a revision of the concepts. And I will also say that I'm not fully perfect in these concepts, so I'm not like a lecturer or fully qualified to teach these concepts, uh, but I do understand a lot of the stuff in it. So now, yeah, so no, I already went through this book several times and I have highlighted and made some notes, as you can see. And that's what I will be focusing on as I go through this now. So, ironically, abstract and formal tasks are among the most difficult mental undertakings for a human being that are among the easiest for a computer. Yeah, so it says the same thing that what I said here. So, what is intellectual or rational, whatever involves calculus, or difficult mathematics is the easiest for a computer, but intuitive and common sense stuff are the hardest for a computer, and and it's a reverse for a human being. So, and also a computer can reason about statements in these formal languages using logical inference rules. Now, logical inference rules are a bad way to design machine learning or an artificial intelligence algorithm. So, what I would say, so this is known as the knowledge based approach to artificial intelligence, and it's not efficient at all. So people have tried it. So basically, the artificial intelligence programs like uh, CYC something, it was an ancient like in an AI program from the 1960s or 70s. So that was designed using this simple if else rules and uh, huge complication in that. And they have logical inference rules and some basic natural language processing, and they have a knowledge base, and that's how they work. And it's a very inefficient way, and it's what we call as kind of a brute force approach. It's not even brute force approach. It's the naive approach to AI. So what we actually need is an AI which can understand concepts and which can learn things. So this was the idea of Turing. So Turing said that one of the ways that you can design AIs is by making them learn the concepts. So the concept is called something like child concept. So you design a child or a seed or a or an infant AI, which will then learn the concepts and then develop. Because that is exactly how intelligence works in this nature as we see. So that's how cats work. That's how human beings work. Now, although there's huge difference between human beings and other species, but basically, uh, although although a lot of information is already present in our DNA, uh, uh, but uh, we still do learn after our birth. We learn a large part of our knowledge after getting birth. So that's how intelligence works, and that's how Turing proposed first. I learned Turing. So going to the next page, the choice of representation has an enormous effect on the performance of machine learning algorithms. So now you must realize that the whole artificial intelligence and deep learning, machine learning, they're all part of a bigger concept or a bigger field called representation learning. So they all come in under this uh, area of computer science or whatever. So so this is the formal definition of deep learning given by the authors in this book. Deep learning solves the central problem. Okay, this is not a definition. So deep learning solves the central problem in representation learning by introducing representations that are expressed in terms of other simpler representations. It's kind of it's kind of like dynamic programming, if you will. So basically, you are trying to uh, approach to this problem of representation learning by introducing representations that are expressed in terms of simpler representations. So breaking the representation into smaller representations. And the quintessential example of a deep learning model is the feed-forward deep network, or I also call it MLP. So MLP is exactly what you call as a neural network these days. So this was the first name coined by some the pioneers of this idea of neural network. We call them neural network mostly these days, but into desired first, this is what it was called, multi-layer perceptron. Because it is not always clear when these two views, the depth of the conceptual graph or the depth of probabilistic modeling graph is most relevant. So different people choose different sets of smallest elements from which to construct their graphs. There is no single correct value for the depth of an architecture. There is no single correct value for the length of a computer program. According to the authors of this book, machine learning is the only viable approach for building AI systems that can operate in complicated remote environments. Deep learning is a particular kind of machine learning that achieves great power and flexibility by learning to represent the world as a nested hierarchy of concepts. Each concept defined in relation to the simpler concept and more abstract representations computed in terms of less abstract ones. So we're basically in deep learning, we're basically breaking down the concepts using the hierarchy of concepts, and each concept is defined in less abstract concept. So that's how deep learning works. Like I said, it's kind of like dynamic programming. And so who should read this book? So yeah, so this is the whole map of representation learning and how where the deep learning comes in. So okay, so I was wrong actually. So representation learning is a subfield of AI. So AI is the bigger box, and machine learning is a kind of AI, and representation learning is a kind of machine learning, not a kind of machine learning, but a subfield of machine learning. And deep learning is a subfield of representation learning. So And this is a different explanation of the same. Now, how rule-based systems operate. So rule-based systems operate whereby you give the input and there's all the annotation programs, for example, psych, like I said, and it gives the output, and uh, this is what the good old-fashioned AI did, also called as GoFi in the 60s and 70s. And classical machine learning, a slightly better approach, would involve the input and design features. So it still does have design features, and then mapping from these features and output. So and the evolution of that would be input, you give the input, and then you extract the features from the input, and then map the features, and then it gives the output. So deep learning is just a better version of this. And as you can see, representation learning is comes here. So in deep learning, you give you see the input, and you break the input into simpler features. Like I said, it involves hierarchy of features and additional layers of more abstract features. So hierarchy of features, and then where you break features into simpler features into lesser abstract ones, and then mapping from these features and then the output. So this is classic ML. This is just this is more modern ML, and this is DL, deep learning. Now, coming to historical trends in deep learning, so learning the rich history and all that. So you can read the history part. It's quite interesting. I would highly recommend some videos on YouTube which go through the history in a better way. So this is the overview of this book, an organization of this book, and many names. Like I said, the multi-layer perceptrons are now called artificial neural networks. Nowadays, we don't even use the word artificial; we just call them neural networks, as you might be familiar with it. So this goes through the history of the deep learning again. So there was first wave, and then there was wave 2 and wave 3. So in wave 1, as you can see, uh, adaptive linear element Adeline. So this was one of the first ones, first kinds of deep learning. And but it's true that deep learning researchers are more likely to cite the brain as an influence that researchers working in other machine learning fields such as kernel machines or Bayesian statistics. One should not view deep learning as an attempt to simply simulate the brain. So this was also said by Ilya Sutskever and also Jeffrey Hinton. We are not exactly trying to simulate the brain. Okay, so we are just trying to draw some concept from the brain, like the neural network and the neurons, so to say. And the neural network is kind of like how the neurons and the natural neural network is in the brain, but it's not. We're not trying to simulate the brain. So that is an important concept. So modern deep learning draws inspiration from many fields, especially applied to fundamentals like linear algebra, probability, information theory, and numerical optimization. So even though we do draw heavy inspiration from the brain, we're not trying to simulate the brain because that would be impossible. Maybe that's the wrong approach because if you see the airplane, uh, an airplane doesn't exactly flap its wings now, and also the submarine does not swim like how the fish does. So, and your car doesn't have four legs, and it does not run like the animals. So we humans design things in a way which is different from how they are in the nature. So you should always focus on the goal. So what are you trying to do? If your goal was to simulate the brain, then you may try to draw all the inspirations from the brain, but that's not the goal here. Here we are trying to develop intelligence. So intelligence is the goal. Uh, so you can draw inspiration from anywhere. And we did take away inspiration from the brain, but trying to replicate the brain may not be the best path towards intelligence, which is our goal. Now, one of the concepts is called distributed representation. Hinton et al. Where that each input system is represented by many features, and each feature is representation of many Western inputs. For example, Suppose we have a vision system that can recognize stars and birds, and others can be yeah. So distributed representation. So this is the key concept of deep learning, and the concept of deep learning is central of this book, and will be described in later in greater detail in the chapter 15. So that was the first wave, and the wave two happened where we developed projects like CFAR dataset, uh, and there was wave three, and yeah, so we are in wave three, and coming to increasing dataset sizes. Obviously, dataset sizes increased as the computers became better, and we have increasing model sizes as well. Biological neurons are not especially densely connected. Number of connections per neuron that are within the order of magnitude even mammalian brains for decades. So in terms of total number of neurons, neural networks have been astonishingly small till quite recently. Unless new technologies allow faster scaling, artificial neural networks will not have the same number of neurons as the human brain until at least 2050. So the number of neurons in the human brain is obviously immensely larger than what we can actually design. So uh, even though these people are, even though the authors are claiming that we may not have it at 2050, this book was actually released in 2019. So things may have changed now. Maybe we do have the same number of neurons as a brain in inside a cluster, inside a server farm. That's possible. And biological neurons may represent more complicated functions than the current artificial neurons. So biological neural networks may be even larger than this plot portrays. So, like I said, we're not trying to replicate the brain here. Our goal is intelligence and not to create a copy of the brain, which is uh, which is not uh, which may not be that much helpful. So basically, to conclude this chapter, deep learning is an approach to machine learning that has drawn heavily on our knowledge of the human brain, statistics, and applied math as it has developed over the past decades. In recent years, it has seen tremendous growth in its popularity and usefulness due to large part to more powerful computers, larger datasets, and techniques to train deeper models. The years ahead are full of challenges and opportunities to improve deep learning even further and bring it to new frontiers. So that's it for this chapter, and we'll proceed to the maths part. So part one is basically full of mathematics, as we can see in the contents here. We have applied math and machine learning basics in the part one, and part two is where we actually delve into deep networks, the neural networks, and all those things. So we will discuss about the part one in the next video.